Hello, this is Paul from First Attack. In this video, let's prove Theorem 4.4.1. Determine if vectors are linearly independent. Okay, suppose S is a set of vectors, including R vectors in the general vector space. By the definition, to verify S is linearly independent, we have to verify each vector is not a linear combination of the others, right? But this theorem gives us a simple way. Okay, for linear independent, the equivalent condition is only zero solution or trivial solution exists of this linear system. See, that's super easy. So this is super important. Okay, so linear independent is equivalent to this linear. So we just solved this linear system means only zero solutions, or we say is trivial solutions exist. Okay, let's prove. So we need to prove in two ways. Okay, let's look at the first proof A, which is if S is linearly independent, we need to solve the system, find only trivial solution, right? And we have to prove. Okay, so this is the first. Why? We can use proof by contradiction. Okay, if a non-trivial solution exists, and we can find a contradiction. Okay, and therefore there's only trivial solution exists. Okay, let's see. Okay, if a non-trivial solution exists, then we will try to get a contradiction. What kind of a contradiction we can get? Okay, so first let's say non-trivial solution means not all the k equals 0, right? Let's say the first k is not a 0. K1 is not a 0. And then we will have this. We will have K1, V1, K2, V2. Right? Okay, so suppose let's say K1, K2, Kr is a solution. Okay. Now what do we have? We have K1 is not a 0, not 0. K2 and the K3 and the Kr, I don't know, so probably 0. So therefore, we can solve. See, we can solve this V1, right, from this equation. Therefore, after the solve, we get a V1 is this, right? Because K1 is non-zero, this is a linear, so K1 could be the denominator. Therefore, we get this form. Okay, so each coefficient that exists, right, means V1 is a linear combination of the others. What does that mean? It means a contradiction. It is a contradict because V1 should be not a linear combination of the other, because S is a linearly independent by the definition. So here is by the definition. Okay, contradiction means what? Means this is wrong. Non-trivial solution exists. Therefore, only trivial solution exists. So that's a proof for the first part. And then we'll look at the second. Go backwards. We have to prove if the linear system has only trivial solution, and then S is linearly independent. Why S is linearly independent? Okay. Only trivial solution. So S is linearly independent. The same. Okay. So let's prove by contradiction. If S is not linearly independent, therefore S is linearly dependent, we will get a contradiction. The same. Linearly dependent by the definition. Okay. Then by the definition, we have this. one vector is a linear combination of the others, right? Okay, so let's say the first vector is a linear combination of the others. Let's say V1 is a linear combination of the others. So we will get this. V1 should be linear combination of the others. So this coefficient K2, K3 to Kr exists. Okay, no matter it's zero or non-zero. Now, see, we move this V1 to the right side. Okay, so we can make a linear system like this. Okay, so what does this mean? This means that the linear system has a non-trivial solution because, see, the first coefficient, at least the first coefficient is not zero, right? So here is non-zero. For the other vector, for the other coefficient, I don't know. Okay, probably a zero, but this means the system has a non-trivial solution. Non-trivial solution exists, right? At least one non-trivial solution exists. Is this a contradiction? Yes. Because it says only trivial solution exists. Now we get a non-trivial solution exists. This is a okay. So therefore, what do we have? Therefore, our hypothesis is wrong. So S is not a linearly dependent. Therefore, S is a linearly dependent, right? S is not is linearly independent. So S is linearly independent. Okay, so that's the proof. Thank you.